Hello, everyone, and welcome to our presentation on a Luminance-Aware model of Judder perception. My name is Alex Chapiro, and along with my collaborators, Robin Atkins and Scott Daly, we did this work at Dolby Laboratories in Sunnyvale in the Applied Vision Science team, although I no longer work there. Here's the recording policy. Feel free to pause if you'd like to read it. So let's begin with the presentation proper. The first question would be, what is Judder? It's in the title of our paper. So with that, let me show you this video of a panning camera sequence across these buildings here in Sunnyvale. And if you focus on the windows of the buildings, you can see there's something strange about their motion. This is a perceptual artifact for digital presentation on a display, where the motion looks a little strange and it kind of goes back and forth and so on. According to prior art, it can be broken down into these subcomponents, such as non-smooth motion, false multiple edges, edge flickering, and motion blur. The next question then is, why does judder happen? We can think of that by comparing continuous motion with the discretized motion on a display. If we have an object moving continuously in the real world, like this bar is moving left to right here conceptually, we could plot out its position as shown here. So it would be a continuous graph of position versus time. On the other hand, if we have discretized motion, simulating that same case on a display, what we're actually showing is a quickly succeeding case of just static versions of that bar. So if we create the same plot of position versus time for the discrete presentation, we would get something that looks a bit like a staircase like this. Now, if you overlay these two plots, we see that although it's, the discrete case is a representation of the continuous case, but they don't match perfectly. And in fact, there are some mismatches there where the bar should have been, but wasn't, or where it wasn't, but it actually should have been. So essentially, this is an artifact that happens because of the differences between the discrete and continuous cases. Now, intuitively, if we increase our frame rate, we could potentially get a better representation of that motion and thus less of a mismatch. So what follows then is, what are the factors that affect judder? Well, of course, there's the temporal sampling or the frame rate, which we just mentioned, but there could also be other factors. In some related work, for example, this work on the window of visibility by Bo Watson, there's an analysis done on the spatio-temporal contrast sensitivity function, where other factors are also mentioned. For example, speed and spatial frequency. If we think about the spatio-temporal contrast sensitivity function proper, like the one shown on this plot from a model by my collaborator, Scott, we can see that it also operates on contrast. That's actually the variable that it's defined on. So we can expect contrast to also play a role. Finally, what you see here on this plot is two versions of the spatio-temporal CSF overlaid with each other for different adaptation luminance values of 1 and 100. And you can see the sensitivity actually more than doubles for the brighter case, which is shown here in blue. What that means is that when stimulus is being presented on different displays with different brightness characteristics, we might be more sensitive to the artifact in some of those cases. So that's something we'd have to keep in mind. For this specific work, we were particularly interested in the motion picture industry, so movies. And we asked ourselves questions like, how do movies treat factors like frame rate? Of course, we know that the standard frame rate for most movies released in the cinema and so forth is 24 frames per second. But some creators have experimented with other frame rates. For example, Peter Jackson and The Hobbit released in 48 frames. Some of you might remember that. And there was also some controversy at that time about the look of that movie. And it looked different than other movies. Certainly it had less motion artifacts than other movies because of its higher frame rate. But there was also this discussion on the soap opera effect and this question that the smoothness of that movie was unpleasant to some audiences. Further, besides frame rate, there's also this idea of speed. When we talk about speed in the vision science context, we typically think about it in terms of degrees in the visual field. And of course, that could be calculated for a display like the case shown here, if you know the size and distance of the display from the observer. Of course, displays can have different sizes and distances. But in this work, we just go by the ITU recommendation of 3 picture heights, which kind of sidesteps this issue a little bit. When we also talk about speed and how content creators and directors think about speed, there are some rules of thumb that they follow, and possibly the most important one is the 7-second rule. This rule says that no object should cross the screen in less than 7 seconds, otherwise you might risk some unpleasant judder. The reality is a little bit more complex than that, but this is probably the most common version of this rule that one might hear. Further, there's this question of brightness. We know, for example, that traditional cinema has a certain spec by the DCI, which typically involves a maximum brightness of 48 nits. On the other hand, this laptop, for example, that I'm using to record this presentation is a MacBook. It actually goes up to 500 nits. And finally, some high-end televisions, just for home theater, could go up to much higher values, such as 1500 nits or even more. So there's quite a lot of variation here in the ecosystem. In that sense, when we think about Judder, if we think of it as this univariate artifact, then there was some original version of the content, let's say for the movie, that was vetted by everyone and it was approved by the creators and everything. And that's the cinema original that has a certain artistic intent for its motion. When that original content is being displayed on a different display, for example, a very bright home theater, because of the added brightness, our sensitivity goes up, and then potentially the artistic intent might be infringed upon, and it might end up having too much jitter. On the other hand, a lot of these televisions will have things like motion interpolation chips. And so they might actually interpolate your content to a higher frame rate, typically just a constant frame rate. And in that case, the artistic intent will be infringed upon in the other direction, where the motion characteristics are different because they're smoother. Our goal here then is to create a practical but simple model of Judder for cinematic content with this goal of preserving artistic intent mainly. We target panning shots, which are notoriously juddery, like the shot that I showed you in the beginning of the presentation. And our method here is to gather data using perceptual experiments, so we learn a bit more about Judder. To do that, we have to create an experimental setup where we can show high frame rate content in a very reliable way. What we did for that was we used an LG C7 commercially available OLED television that can show stimuli at 120 Hertz. We used some photosensors from Thor Labs attached to an oscilloscope that can take very fast measurements of our display, and we can produce plots like the ones seen here to see that there weren't any hiccups with the presentation. And finally, we had to create our own custom OpenGL GPU video player implementation, because we found that most commercial video players just aren't able to show really high frame rate content reliably without ever dropping frames or interpolating or something like that. And we didn't want our participants to mistake those things for the artifact we were looking for. Our experiments consisted of showing participants panning video sequences. For example, here's one being shown now. This is a moving edge. One thing to note is if you see any quantization artifacts, this is due to the video here, but it was not present in our original experiment. It was very clean images. After a training period, we asked our participants to rate Judder on a scale of 1 to 10. Let me tell you about the first experiment here. We showed participants the moving edge that I've just shown you and used the following variables. For frame rate, we showed 30, 60, and 120 frames per second. For luminance, we used an average of 2.5, 10, or 40 nits. For speed, we had 17 second pans, the slowest, 11 second, and 5 second pans across the screen. The values in degrees are shown there as well. And finally, we had Michelson contrast as one of the variables at 0.5, 0.75, and 0.95. We decided not to go lower with the Michelson contrast because we felt it wasn't realistic for cinema applications to have very low contrast images. Here are the results for this experiment. The first three variables, frame rate, luminance, and speed, were found to be statistically significant, but contrast was not. So in these plots, we average out over contrast, and we get these results. Let's analyze these plots, starting with the one on the right. The three lines represent the different luminance cases. So we got blue for 40 nits, green for 10 nits, and red for 2.5. The plot on the right is the 120 frames per second version. The x-axis showing speed increasing towards the right, and the y-axis showing Judder, which was what the participants were rating. This plot actually isn't very interesting because there isn't a lot of Judder, so participants just didn't see a lot of Judder in the 120 FPS case. Now the plot in the middle shows the 60 frames per second case, and here there's a little bit more information. The blue line for the higher luminance does have this increasing trend of Judder, but still there's not too much Judder to talk about. In the 30 FPS case on the left, however, there's a much more interesting scenario. We see this really nice separation between the three lines of different brightness levels. And we also see a clear positive trend with more speed generating more Judder, which is all pretty intuitive and kind of follows our prior knowledge from the related work. We then followed this up with a second experiment. Because we found contrast to not be significant, we replaced it this time with a different variable, images. Everything else was kept the same. And what we showed people was, instead of that moving edge, we showed them these panning images. The first one was this gas station here. The second was this picture of a thorny cactus plant, which is a more natural image with these diagonal lines. And finally, we showed them also a still from Big Buck Bunny, which is, of course, an animated image by Blender Foundation. Here are the results for the second experiment. The first three variables, frame rate, luminance, and speed, were once again found to be significant, and images was not found to be significant. So these plots average out over that. Once again, the 120 FPS and the 60 FPS plots don't have a lot of judder, but the 30 FPS version, once again, shows us a similar result as last time, with this nice clean separation between the different brightness levels and the increasing trend of more judder with more speed. For the third experiment, we did a couple of changes. First, we changed the frame rates. So we noticed that the 120 FPS case didn't have a lot of judder, so it wasn't giving us much information. So we removed that one, and instead we added 24 frames per second, which is a really interesting case to test because that's also the standard in the cinema. Luminance and speed were kept the same, but the final variable, we chose it to be shutter angle. So shutter angle could also be thought of as a version of blur, and we wanted to see what kind of photorealistic blur could be incurred, let's say during the capture process, and would that make a big difference for perceived judder in our experimental setup? Here are some versions of that. Oh, you might also notice that the shutter angle is sometimes set here to 0. That's a nominal value for our still frame. The way we obtain these panning shots is by panning an image inside of a larger image, by panning, a view inside of a still capture. So we just nominally say that that is 0 degrees shutter. Here's the image that we used for the study, which is the thorny cactus plant at 0 degrees. That's the sharp version. And here's the simulated version for a 360-degree shutter. This is done in linear luminous space, and it just simulates the type of blur that would occur with the camera moving at that speed. So I'm going to go back and forth between these two a couple more times. You can see this is the sharp and this is the blurrier version. Although it does add some blur, but the blur isn't completely removing the features. It certainly maintains most of those edges to be super threshold and so on. Here are results of this experiment. Once again, we find that the first three variables of frame rate, luminance, and speed are statistically significant, and shutter angle was found to not be significant in this case. So we average out over the variable, and we get the results as follows in the plot. The plot on the right for 60 frames per second this time does not have a lot of judder. When we move to the 30 frames per second case in the middle, we see the nice separation between the lines and the positive trend with speed as we expect. And the 24 FPS case on the left has, once again, similar characteristics, even more of a separation between the 2.5 nits and the other two cases, and a positive trend with speed as well. In order to create our model, we combine the results of experiments 1, 2, and 3 into a model for judder. The significant factors that we used were frame rate, luminance, and speed, as found in our experiments. We do change some of these variables. We change frame rate to frame duration, so that's 1 over frame rate, and we change luminance to log luminance because it more closely approximates the human visual system. We fit a quadratic polynomial to our measurements, such that judder is predicted by a polynomial of degree at most 2 in these 3 variables. This is a good fit to the data with a mean error of 0.24 on judder, or 9.4% average error per sample. Here's a view of our model. Of course, the model to be fully represented would be a 4-dimensional function, right, with 3 inputs. So this is just a slice of it with the speed set to 7-second pans, like that important rule that we mentioned before. The vertical bars depict 95% confidence intervals. And I'd like to call your attention here to the inset on the slide. This inset is just the top view of our plot, and it shows an iso judder line for the 7-second rule. So we can think of the 2.5 nit average luminance as being representative of a cinema context. And what we have here is that the judder for a 24 FPS 2.5 nit case lies on that red dot on the bottom left. As we trace this line, we see that if the luminance were to be increased to 10 nits, which could be representative of, let's say, a home theater case perhaps, then the frame rate to keep the judder equivalent for the speed would be of about 31 frames per second. That's some interesting information that we didn't have before. Here's another view of our model. This is, these are 3 slices for different speeds, 17, 10, and 5-second pans. We see here that the judder does increase with a higher speed as expected. So this all makes sense. And we can look at that inset as well, where we have a cross-section at 24 frames per second of this model. Now here, there's something interesting. The 5-second pan would normally be considered a little bit fast and kind of dangerously juddery, perhaps, for the cinema case of 2.5 nits. But as we increase the luminance, we notice that for something just under 10 nits, we would have an equivalent speed of 10 seconds. And if we go up to 15 nits, we would have an equivalent speed for that pan of 17 seconds. That means that as our display technologies evolve, we might reach points where content creators are severely limited in the types of motion they can show on a display if they continue to use 24 frames per second as their standard. And the 7-second rule might then be updated to something even greater than a 17-second rule, and that's a very slow pan indeed. Finally, we've created this model, but we also validated it through a validation experiment. What we did with this experiment was we showed reference videos at a low frame rate, test videos at a high frame rate, and participants had to match the judder between the two by controlling the brightness of the high frame rate test sequence. Here are the sequences that we used. These are camera pans from this one from Big Buck Bunny from Blender Foundation. And you can see they're more complex than the ones that we used to build the model. So they have color, they have speed that isn't always uniform, different types of more complex motion, and so on. This is a shot from Nocturne by Netflix. You can see the judder on the white ballerina dresses against a black background. And finally, we have a different shot here with the kid dancers from the same movie, Nocturne by Netflix. Here are the results of our experiment. On the right, you can see a table with all the cases that we've examined. We have the reference luminance, the reference frame rate, and the test frame rate. And we've experimented cases of 24 FPS compared to 30 and 30 FPS compared to 40. In the center, you see the results of our experiment. In red are the selections made by the users with the confidence intervals shown with the vertical bar. In purple, there isn't another model of judder to compare against. So what we did was we adapted the Ferry-Porter law and added a free term to it as well, so that we could try to use it to predict judder. The Ferry-Porter law, of course, originally is meant to simulate the critical flicker fusion threshold. So it doesn't take speed into account, only frame rate and luminance. We see here that our model outperforms the Ferry-Porter law in every case and falls within the 95% confidence interval in all cases but one. So let's take a minute to talk about applications here at the end. Our model can be used to predict perceived judder. For example, here's a simple application. We can simply flag juddery shots in movies. What we did here was we broke down the Big Buck Bunny short into shots. And for each shot, we've calculated the frame rate, which in this case is constant, the mean luminance and the mean speed. And we've applied our model to it. One thing to remind ourselves here is that this is a polynomial model. So if you want to apply it to variables that go beyond the ranges that were tested in our experiments, you have to be careful about how you extend that. So it does not necessarily extend gracefully beyond those limits. Finally, this model could also be used, for example, to inform choices for tone mapping and to match judder between different cases, let's say different frame rates, through changes to the brightness. With that, we're reaching the end of our presentation. I'd like to run through some conclusions with you. So we've gathered psychophysical data on judder. We've varied relevant factors using simple stimuli. We've validated our results using more complex videos. This is the first model predicting the magnitude of perceived judder in a video. We've generated here some valuable data that can provide guidance to content creators. For example, by updating legacy rules of thumb, like the 7-second rule, for different types of display, perhaps. This information is also useful to display manufacturers and content providers to inform them on choices and interplay between things like brightness and frame rate and speed and so on. Some quick comments about our work and some future work. This work focuses on camera pans and may need to be extended for complex motions, variable speed rates, and so on. There's a really interesting area of future research, which is the spatiotemporal contrast sensitivity-based predictors for superthreshold differences. And it's really exciting, although it might have some difficulties for practical application because of the heavy computational cost. It typically requires a Fourier transform on a large video block, which may sometimes be challenging. Finally, we modeled judder as a whole, but as I mentioned at the beginning of the presentation, it can be broken down into these perceptual subcomponents. And that's also an interesting avenue for future work. With that, we've reached the end of our presentation. I'd like to mention that this work is available on my website, Chapiro.net. All of our experimental data is also available online, so feel free to use that for your own work. If you have any questions or comments, please feel free to contact me at my email, alex@chapiro.net. And with that, thank you very much for your attention, and that's the end.